research. Yeah, so great. Okay, great. So before we start the real topic of my introduction to the research, but I just want to quickly give you the quick introduction about my research group at KIT, Karlsruhe Institute of Technology. So Karlsruhe, located in the southwest of Germany, is really close to bordering with France, and then not too far from Switzerland as well. It's a quite nice place to visit because you can combine like France, Germany, and then Switzerland. But anyway, so our institute is called Intelligent Sensor Actuator Systems, or we call it ISAS at KIT. So Professor Hannabeg is the head of the institute. We have 2 postdocs, 9 PhD students, and the 4 technical and administrative staffs. These 2 figures kind of main or core research topics of our institute. The left one is, I mean, it's obviously very popular application that we do some control stuffs, especially for the model predictive controls. The right-hand side, I'm not really sure if it is really familiar, but we call them deterministic sampling, or like LCD samples. So basically what we want to do is we want to sample from the certain density or distribution with a deterministic way, so that it's not really random, and as you can see, it's kind of nicely distributed. That's the main 2 research topics that we have in our institute. And one of really interesting project we have is, I'm not really working on this one, but it's really nice video that you have here. So we have quite big room, just about the size of this room. We have a haptic interface, so you can just control this haptic and then do some how do you call the remote operations or something. For example, all the arguments, reality as well. So it's quite interesting topic we have. And so another research topic we have is this sorting motion. So when we want to sort the bulk materials, for example, this case of corns and beans, so there's a flaps so that it's flapping away and is controlled by the MPC. Or these days they're trying to use some like reinforced learning as well for these kind of controls. So those are kind of interesting application or project we have at ISAS. Yeah, it's quite awesome. Those are actuators. Move on. The other things is the deterministic sampling. This is interesting research topic as well. So if you think about the random samples, what we usually use in the real world cases were like the state of the practice, let's say. The problem is, as you can see on the here on the right top figure, whenever you want to deform the density or the distribution, if you use the random samples and then the number of samples are not is not big enough, then there could be problems where some holes or like some clusters can be there, which is not ideal. But we wanted to use these kind of deterministic samples on the bottom line, which is really nicely distributed. And then when we deform or transform the desired density, then obviously this representation is much better than the random samples. So those are another research topics, and this is what I do at ISAS. So we call it particle flow-based filters. The main concept is literally we want to generate the flow of the particles to move on to the posterior instead of using like a reweighting or weighting and importance weighting in the particle filters. So so today's talk is more or less about this one. So yeah, let's get into that. So this part I call the Hitchhiker's Guide to the Particle Flow-Based Filters, a survey. If you're a big fan of Hitchhiker's Guide to the Galaxy, probably you are already kind familiar with this title. Yeah, because if you read the novel, it's about like uh, there's a small book, the guiding and the giving all the information about the galaxy and everything. So it's inspired by that one. So this will provide some overview and then some details, and then quick way to the research direction. What if you're interested in this field? And I prepared this work for the World Congress, IFA World Congress, which it will be next week in Busan. So this is based on the paper, but more into the detail. Then some of the details will not be actually discussed in the World Congress because the time limit there will be like only 20 minutes, but I have slightly more time here. So anyway, um, so yeah, this is some overview. We have three main algorithms shown here. The first one is a Newton flow particle filter, which is proposed by Professor Hanabeg and our research group. The mid one is a local exact flow Dam and Huang filter. As you can see from there, that is already proposed by the researchers named Dam and Huang. And the last one is a feedback particle filter with diffusion map. So yeah. So why do we need a guide? This is the first research question. Why do we even need the guide? Because apparently I think these particle flow based filters are quite strong and really interesting research topic, but it seems like only some of the researchers or research group are working on this and not really widely introduced. And then why do we need these particle flow-based filters? So if you are already familiar with particle filters, these two are the obvious limitations of the particle filters. So because we do the Bayesian theorem can be written like a posterior is proportion to likelihood times prior. But the prior, when the problem is when the likelihood itself is quite narrow, and the overlap between the prior and the likelihood is small, then the prior samples will degenerate. That's the problem. So as you can see on the top figure, the red ones are degenerated particles, and the only two samples in this case are remaining for the next time step, which is an idea. Well, the well-known solution for this one is just we can do resample. And the problem is even though we do resample, all the particles will be concentrated only in certain area. Okay, fine, we can do the jitter as well, that we can spread out some particles, but there's a limitation. It's not really ideal. So this is the problem for the particle filter. And the main idea of the particle flow-based filter is instead of we doing this, weighting, importance weighting, and the reweighting, why don't we just move or migrate the particle to the posterior region? If you Does anyone actually have some idea which is similar to this one then? Like instead of waiting, we do um, move the particle to the posterior. Actually, there is another algorithm. It's not really flow, but quite similar. Um, Anyone actually know that it is something common filter? Ensemble comma filter, maybe some of you already know. So ensemble comma filter has kind of similar concept. It's still we use the comma filter comma again and update steps as same as EKF, but they use the member of ensemble members, so similar to the particles. Then we move these ensemble members to the posterior using this command again. So if you're already familiar with the ensemble comma filter, this is kind of similar, but the difference is ensemble comma filter is one step, just one shot update. So you just multiply by the command gain, and then the state will be moved to the posterior. But this one is flow, so it will give you kind of flow with the artificial time. So yeah, that's the difference, but the similarity and the difference between the ensemble comma filter and then particle flow filter. So the key idea of the particle flow filter is the progressive inclusion of the measurement using homotopy continuation. So what we want to do is instead of we use the measurement with the likelihood, at one time. We want to divide it into smaller section, and then we use this measurement to make the progressive or like inclusive way of the measurement updates. And then we use the homotopy. I'm not really clearly, I don't really have a clear idea of what the definition of the homotopy in mathematic way, but the homotopy here is that we start from the prior, and then the final point we want to go is the posterior. So we can make multiple ways to go from prior to the posterior. That's the homotopy concept here we have. So this homotopy or the progressive inclusion of the measurement will induce a flow of the particles to the posterior region. That's the main idea. So yeah, there are tons of papers out there actually, but not really many of them are very well known, and some of them are quite known, but not everything. And so in total, there are 117 papers that I reviewed, but for the conference paper, I only included 69 papers. And then there are actually many duplicated papers as well. So I think this survey or review will give you quite nice idea what kind of approaches are there, and then which can be applied for your applications like that, and then like comparison in the numerical simulation as well. So we categorize into three main groups. The first one we call progressive Bayesian filters, or in short PBFs. It's from Hanobek's group, which is our research group, and the second one is Daum and Huang filters, named the DHF. It's from Daum's group, and then some other approaches are from the other research group as well. And then last one is the feedback particle filters, shortened as FPFs, and it's mostly from the Meltas group. So one of the most important idea from these particle flow-based filters is the artificial time, or sometimes they call the homotopy parameter as well. So if you imagine a discrete time system from t-1 to t+2, whatever, and let's see the exact time, discrete time step t. So the homotopy idea is at time step t in a discrete time system. Let's say it starts from a gamma equal to 0. Let's say the gamma is the parameter for the homotopy continuation, and there will be a gamma plus delta gamma, and then plus 2 delta gamma, and up to 1. So this is the reason I draw this one in the vertical axis, is because it's not really you discretize between t and t+1, but instead it's artificial time-like parameter only for this homotopy continuation. It will be much easier if you see the equations to understand this concept. So the key point here is there is a time-like parameter, which is not real physical time, but it is not really dividing the times in between the time step, but instead of it will happen in each time step. So for example, we have a gamma equal to 0 to 1 at time step t, and then at time +1 step, there will be another gamma equal to 0 to 1 as well. Also, gamma here is I just showed in a discretized way, but it could be continuous as well. And the main concept, one of the main idea of this particle flow-based filter is this progressive inclusion of the measurement using homotopy continuation. So if you see here, so we want to calculate the posterior. Here, the notation is probably slightly different from what you usually use, but in our institute, we use Fe as a posterior density, and the underbound is vector. So we define this posterior density of X with a function of gamma, which is artificial time, which I just introduced. And so basically this is the Bayesian theorem, but here we define the likelihood function as a function of gamma as well. And this is the prior, FP is the prior. So this is one case, the most common case of how we define the likelihood function. Imagine we have gamma is 0 to 1, when gamma is equal to 0, then this will give you only prior. And when the gamma is equal to 1, this will give you the final form of the Bayesian theorem. So just changing this artificial time coefficient or parameter gamma from 0 to 1, you actually can make this the Bayes theorem changes. That's the main idea. So how we this is one example, not normalized, but so don't really care. Please don't really care about the area, but let's say we have a likelihood function when gamma is equal to 0, means it's not really non-informative. When gamma grows, then at final step we will have the exact likelihood way what we wanted to use from the beginning. So this is the concept of homotopy and the artificial time. Okay, so there are key papers. So there are tons of papers about this topic, and then we just selected these as a key papers. So if you want to have a look or more in detail about these researches, you can have a look of these papers. So from the PBF or the Hanabex group, the Newton flow particle filter is one of the state-of-the-art approach they can have a look. And from Dahmer Huang's filter, so Gaussian flow or EDH, exact flow Dahmer Huang, is one of the key paper. And then one of the very fundamental papers, you can have a look at this one. And invertible particle flow particle filter by Cortez group, that's another variant of the EDH. The Gromov flow by Dahmer Huang is one of the latest variant of the Dahmer Huang's filter, which is stochastic. We'll discuss more in detail later. And error flow by Zanetti's group, EFF, is another really important and interesting approach as well. It's from 2025, so it's quite new as well. And then feedback particle filter, there's some diffusion map based one, which is quite interesting from 2016 or something. Yeah, but other key milestone papers from each group can be found in the conference paper, and some histories are elaborated in the conference paper as well. And I like this figure. So we have very high level branch particle flow filters, and then I just categorize in a graphical way so you can understand it more in detail. So the branch here means the three branches I mentioned, like PBFs, DHFs, and the particle flow filters. And groups are not really research group, but the internal group of these research branch. And then the method itself is how they define this flow, but it's not really about the algorithm itself, but it's more like how they define the flow. And the last level is a filter or algorithm, is how they really realize the estimation using this method or flows. So in the PBFs and the DHF and the FPFs are the main three branch we categorized. And from the PBFs, there's one specific filter called PGF42. This is really interesting filter as well, but this is not really particle flow because they don't really use the particle, but it's continuous. They use the continuous density. And as you can see here, 42 is something related to the Hitchhiker's Guide to the Galaxy as well. And Newton flow is another type of flow from Professor Hanabeck's group. And there's a particle filter named Newton flow particle filter, which is the realization of this or implementation of this algorithm. And Dahmer Huang's filters group, there's one big group called deterministic flow. There are multiple flows in this group. One is an incompressible flow, and the other one is an exact flow. And we'll discuss about the exact flow more in detail later. And from the exact flow, there is one specific implementation called Gaussian flow and particle flow particle filters as well. And another branch is stochastic flow. So you can see why there's a two group in the Dam and Huang's filter group because one is deterministic and the other one is a stochastic flow. NZD stand for non-zero diffusion. So yeah, it's basically they enable the diffusion part in the flow so that it can be more or less stochastic. Gromov flow is one of the main algorithm you can find. We'll discuss slightly more about the Gromov flow in the later slides. And there's an error flow filter as well. Feedback particle filter. At the end of the day, the main idea for this one is how they define or approximate the gain for the control part. Because as you can imagine from the name, the feedback particle filter is similar to the feedback controller, and they need an approximation of the gain. So depends on how they approximate. There's one constant gain, and then the other one is a diffusion map. So yeah, let's talk about slightly more in detail in mathematics. Then it will be easier for you to understand this concept instead of just talking about in higher level intuitions. So we start with a homotopy continuation. So this is basically same as we already seen before. Here again, the gamma can be go from 0 to 1. And the key approach is Newton flow particle filter. And what we want to do is, well, at the end of the day, what we really need for the estimation is the posterior density, how the posterior will look like. But the problem is we don't really know the posterior. That's the problem. So what we want to do is we define the reference density here, F tilde, as the homotopy equation, FL likelihood to the power of gamma times prior. And then we want to define the target density, which would be posterior density maybe, as FE, but with the parameterized with the parameter eta here. So for example, if the target density is Gaussian distributed, then eta will be like first two moment, mean and covariance or variance. And if the target density is represented using samples or particles, then it will be like the position of each samples. That's what we really parameterized with the eta. And of course, you can use some other way as well. You even can use normalizing flow. So this is target density. And what we want to do is we want to calculate or define the distance between the target density here, FE, and the reference density FE tilde here. So as you can see here, the distance between this reference density and the target density is actually the function of this parameter eta and gamma as well. And so it's quite simple. What we want to do is we just want to find what we really want to find is eta, because we already parameterized this target density with eta. So we just need to find the eta. That's what we need. Then how we do that? Because then what we want to do is we want to take a derivative, and the stationary condition of the local optimization from the previous one will be this equal to 0. The gradient should be 0. And then if we take another partial derivative of this one with respect to gamma, then we'll have eta dot gamma equal to Hessian times the partial derivative of the distance with respect to eta and gamma. So here you have a Hessian, that's why it is called Newton flow, because we have a second derivative. And so basically we want to, maybe if you're already familiar with the homotopy optimization, this form is exactly same as the homotopy optimization. And this is basically an optimization problem, the finding eta that minimizes the distance d. So yeah, that's the main concept. So as we mentioned before, eta itself is the parameter of the density. For example, if it is the case for the sample-based one, the change of eta means change of the position of the particles. So these ODE will give you the flow itself. So how can we solve this one is we just use the ODE solver, then it will give the flow. And then if you just solve this between 0 to 1 with the gamma, then we will give the flow that we want to find, and then we will end it up with a posterior. That's the main idea of this algorithm. Yes. So yeah, X is the state, and the measurement observation is we just define as a likelihood here. So yeah, exactly. So here in the function, well, it's not really explicitly mentioned here, but the derivative of the likelihood will be contained inside of the distance and Hessian as well. Yeah, no worries. Yeah, that was the first main group, Newton flow, and then let's move on to the second group, Dam and Huang filters. Very interesting because actually the homotopy idea itself is first introduced using the homotopy for the estimation is first introduced by Dam's group in 2007, if I remember correctly, but they actually used the same thing but with a logarithm here. So if you remember in the Newton flow, they used the FL to the power of gamma, but they just took the log on both sides. So the gamma is just shown as a multiplication here, and then minus log K is the normalization factor. So the concept is quite similar, but the way they solve these ODE is the different. So we want to define the particle flow as a dx, the change of the state with respect to gamma as a gf. This is what we call flow, particle flow, and again we start with the total rate of change of so this probability is given by the Fokker-Planck equations. And so in equation A, that's the Fokker-Planck equation of this density. And if you use the multi-variable chain rule from the left-hand side, then this will be given. So because it's d gamma, but we just want to change it to partial x d gamma, and then partial log Fe, and then partial gamma here. And the thing is, because here what we want to find is dx d gamma, and then we just want to do some tricks. Here, if you see here, we just wanted to take a partial derivative of the log homotopy with respect to gamma. So basically, we want to take a partial derivative of this one with respect to gamma. And then it will give just log of likelihood because prior is not the function of gamma, but here we have a gamma, so it will just give the log f the likelihood, and then we substitute equation 10 into the previous one. Here you see the partial derivative of log posterior. Then we can just simply substitute to the plus log likelihood. Then using the definition of the particle flow GF here, we just substitute this one to GF. And then if you remember Fokker-Planck equation, d log of the posterior d gamma is equal to the trace, this one. So it's equal to trace. And then this is end up with the partial differential equation PDE as shown in the equation 12. So what we have to do is we just need to find GF here, which is what we want to find, the change of the state X, or in this case is the particles, with respect to the change of gamma. So the general solution of the PDE is given in equation 13, and we can calculate with the 14, but the problem is it's actually not really solvable in the real life. I mean, general solution is there, but you can't really implement in this way. So Dam and Huang proposed multiple ways, but one of the simplest and then very easiest way is, as always, we want to assume the prior and the likely are Gaussian or exponential family. So this is called Gaussian flow because they assume the Gaussianity of the prior and likelihood. and also called exact flow Damian-Huang or EDH filter. So we just use that assumption, and then it will end up this linear combination form. So quite simple, and then it somewhat looks similar to the Kalman filter as well. You just need this covariance matrix, Jacobian. This is not really Hessian, but Jacobian of the measurement model. And then you see here the homotopy parameter gamma here. And the problem is the covariance matrix P itself can't really be calculated by itself, not like particle filter. So sorry, like a Kalman filter. So this filter requires either sample covariance. You can calculate the covariance using the samples, or the auxiliary filter such as EKF, only to track this covariance P. And H here is the Jacobian matrix, and R is the measurement noise covariance. So that was the Gaussian flow. And so the co-test group, sorry, I didn't mention that. So the problem of this filter is they calculate this Jacobian H, the measurement Jacobian H, only at the mean of the samples, which is a quite strong approximation. So co-test group proposed another really simple tweak using the local exact flow Damian-Huang. They just wanted to calculate this H at all the sample points, not only at the mean. So that's the only difference, and that's why it's called local. And now the flow itself becomes sample specific. And another key approach from the co-test group is particle flow, particle filter. They just not just simply move the particle to the posterior, but they just want to use these moved particles as a proportional density, and they want to do another importance weighting. So that's why they have another particle filter at the end. Yeah, and so if you remember the diagram with the deterministic flows and the stochastic flow, so far it was about the deterministic flow, which means if you have a same prior and the same likelihood, the flow will always be the same. But now we want to make it more realistic using the stochastic flow, even though then the prior and the likelihood is same, the flow can be different in this case. That's why it calls stochastic flow or non-zero diffusion. So in the Fokker-Planck equation, now we want to consider this diffusion term on the right-hand side. So if you remember, we just defined the dx over d gamma equal to gf, but now we have this diffusion term. And the key of this diffusion, non-zero diffusion case is to approximate this covariance Q. This is not really a Q from the dynamics model, but it's for the particles propagation, the particles flow. So please don't be confused with the other Q that we usually use for the time propagation. But anyway, if you just simply assume the Q equal to 0, there's no diffusion, then it becomes basically the same as the previous ones, like Gaussian flow. But we want to assume here we have another stochastic term, diffusion. And how do we define this Q is the key of these non-zero diffusion flows. So it depends on how you define. There are multiple approaches, but one of the key approach is Gromov flow. So it can be just simply written like this. So you have the particle flow term here and the diffusion term here. So diffusion term, we just in the real code implementation, what we do is we do the Cholesky decomposition of this covariance matrix, and we just times random number and add it to this flow. Yeah. Again, we need the auxiliary filter here again to estimate the covariance. Yeah. The last one from this group is error flow filter. We still use a homotopy continuation, but they define this flow in terms of the maximum a posteriori concept. So you can imagine the flow is defined by two different flow. One is the mean flow, which moves the mean of the samples. And another flow that define the error of each samples from the mean. So we define two errors here, and then this one start with the Gaussian prior and likely assumptions. So this is basically the prior part and the likelihood part, and we just put everything else into this constant C. Yeah. So normalizing constant, yeah. So what we want to do is we want to define a least squares cost function with a function of gamma here. So as you can see here, gamma, it's multiplied to this likelihood part. So it's basically same as log likelihood with the Gaussian assumption. And so what we want to find is a minimizer of this equation 17 is a maximizer of the previous equation 16. So what we want to, this is basically becomes a maximum a posterior problem. So we want to take a derivative of the Jacobian, then we will, sorry, not Jacobian, the cost function, then the first order necessary condition will be this one equal to 0, and then total variation will give you like this, and then we do some other steps, then we'll give you this mean flow. And likewise, we define the error flow. So as you can see here, error is defined by the particle minus mean. So the difference between the particle, each samples, and the mean as error. And then this DE, D gamma, is the change of this error, not the exact samples, the change of error with respect to the change of gamma is given like this. And again, here for the measurement, just if you're familiar with the ensemble gamma filter, they also have this additional noise term in the measurement. Error flow filter took the same idea here. So it becomes stochastic again here. So you move the mean with this flow, mean flow first, and then we want to move the other samples using this error flow from the mean. Yeah, so that's the last one from the error flow, Dam and Huang's filters. And the last group is Meltas groove. This is quite an interesting concept because quite different from the previous two groups where they used the homotopy equations, but they use this control problem concept, because if you see the right hand side, this term is basically same as the control input of the control problem, and then by just calculating the or approximating this control gain K, this just becomes the optimal control problems. And now it becomes the approximation of the control gain K here. So there are two main approaches. The constant gain, or CG, is just simply they use the Monte Carlo approximation. So they define control gain here, and then DI here is the modified innovation term where you calculate the expected measurement and the measurement. So the problem of the constant gain is gain itself is constant for all samples. So basically all samples will move with the same amount, which is not ideal. So they proposed another approach called diffusion map, which is based on the RBF kernel here. As you can see here, it defines the relative between the two different samples, and then define the diffusion operator, and then using this one, they can approximate the constant gain. So now it becomes sample specific, and obviously it works better. So yeah, just quick summary of these three branches. The progress Bayesian filters grew from Professor Hannebeck's group. The first introduction was 2003, but that was for the continuous density, not really sample-based densities, but the sample-based density first introduced in 2011. Dam and Huang flows filter, they introduced first at 2007 with a sample-based one, and then log homotopy, and then feedback particle filter first introduced in 2011. The main idea is first two, they use the homotopy, more or less the same idea. And then the last one, they use the optimal control, which is the same as a feedback controller, the similar concept of the feedback controller. And another interesting difference is the first two use the discrete time step, but the last one define everything in the continuous time. And obviously, the first two use the homotopy, they use the artificial time. In the original paper of the Dahme-Huang's filter, they use lambda instead of gamma. And the feedback particle filter, they don't have any artificial time concept, but they discretize their continuous system to the smaller dts. And another interesting difference between the first two groups are the progress Bayesian filters group, they can actually use the continuous density as well, not limited to the sample-based one, but Dahme-Huang's filter, they're actually, well, the flow itself is not really limited to the discrete, but most of the applications for the implementations are only shown in the discretized, the sample-based approaches. And another key difference is PBFs, they use the distance measure. As you remember, we calculate the distance between the reference density and the target density, but there's no distance measure used in the DHFs. And these are the key algorithms that I will show the implementation examples. So the simple 2D range only example is simulated for the quick comparison. So you have, let's say we have a radar at 1.0, and then the target is located at 0.0, and then the measurement we have is only range. So range only problem, we get the range equal to 1 here, but we don't have any bearing information, so the measurement likelihood will be something like in a ring shape with some deviation. And then we assume the mean of the prior is located 0.0 as well, and then like this, I will show another figure later. So what we expect for the posterior is still kind of the ring shaped, but more concentrate on this target area. So we tested only for the one time step obtained, which means we didn't really consider the time prediction at the moment. And the artificial time is defined as 0 to 1, 0 to 1. But key difference here is a Newton flow particle filter. We don't really need to define the artificial time delta gamma, because it will be just selected by the ODE solver. ODE solver will just give you that. But Dahme-Huang's filter requires the really well-designed exponent, the artificial time steps, like how do you define the delta gamma is really important because of the steepness of the ODE. And actually, that's another really interesting research topic where there are tons of papers about that as well. And error flow filter use the ODE solver, so that we don't really need to define these specific gamma steps. We use the 100 particles, and then for the prior, we used the two set of samples. One is the deterministic set, and the other one is a random set. And as we mentioned, DHF requires the auxiliary filter, so we use the EKF for the DHF, and nothing else for the other ones. Everything is implemented Julia. Yeah, that's the filter setup. So the priors look like here, like this, likely something like this. I mean, you can see there's really small deviation only in the likelihood, which means that we really trust the measurement. And then what we expect for the posterior will look something like this. As we can see here, around the target, there's more likelihood, it will be more likely to be around this target area, but still little bit of posterior is remaining on the right-hand side as well. So the problem of the particle filter is these two examples using the particle filter. Last one is using the deterministic prior sets. Well, the deterministic prior set here means that there's another sampling technique in our research group proposed. It's like nicely distributed prior. And then the right-hand side is the random samples. But if you don't really have a good enough number of samples, then as you can see on the right-hand side, is not really ideal. So this is particle filter problem. Degenerated samples and progression after resampling. That's the issue what we want to handle. So these are results from the LCD prior samples. So on the left-hand side, and then Newton flow filter, and then the right-hand side is the exact flow Damian-Hong filter. As you can see here, when gamma changes from the 0 to 1, it nicely form the flow. So this is one discrete time step update. So the gamma there is not really the physical time, but it's an artificial time for this ODE. But really interesting result from the EDH here. This is happening because the Jacobian at the mean just becomes -1 and 0 for this case, which is not ideal. But luckily enough, the local EDH, which calculates the Jacobian for every sample points, it solved the problem. And PF, which use another importance weighting after this flow, actually shows it looks good, but it's not really nice because as you can see here, it doesn't really contain the proper uncertainty, so it's overconfident. That's the problem. So Newton flow works okay. EDH didn't really work. Local EDH works okay. PF was just overconfident. And the Gromov flow and the error flow filter, as you can see, also kind of stochastic, but it still looks okay. Works okay, and then error flow filter also works okay-ish as well. Feedback particle filter with the constant gain didn't really work well because they just assume the constant gain, and then after a few steps, it doesn't really update the gain and doesn't really work well. But the diffusion map based one, which consider the distance between the samples, actually work quite well as well. And a random prior sample set case is quite interesting as well. Newton flow, unfortunately, didn't work really well for the random samples. And EDH case, it showed a kind of similar tendency like the previous case. Local EDH, it works again quite well. And PF showed a similar tendency, which is overconfident and it underestimates the uncertainty. And Gromov flow and an error flow filter worked okay. Yeah. And again, the constant gain one didn't really work well. And then diffusion map one worked okay as well. Another interesting example for this 2D range only example. So it's basically same setup, but we just wanted to check what would happen if we have multimodal prior in the far away to the left. So likelihood will be the same because we just use the same setup. Then now the posterior will look somewhat like this. It should be biased to the left because the prior was far away to the left, and then these two prior should be merged into one posterior like this. So this is what we expect from the filters. Newton flow filter, it looks okay. It didn't really shape like a slightly tilted, more like a banana shaped, but it shows like slightly biased estimate. And EDH, the only problem was there was no flow to the X2 direction, but it's still, the mean should be somewhere here. So the mean estimate is fine, but the problem is it didn't really merge into one distribution. LEDH, local exact Damian-Hong worked okay-ish as well. But again, the problem is they didn't really merge into one. And the particle flow, particle filter, again, they show too small uncertainty, which is not ideal. Gromov flow and the error flow filter, they works okay. And this is really interesting result from a Gromov flow and an error flow filter, because if you see this Gromov flow, the mean would be almost same as the target. So in terms of estimation, the error will be smaller for this case, Gromov flow filter, because the mean of the estimate will be almost same as the target location. But the problem is the rear posterior analytical solution of the posterior should be somewhere to the left slightly because the prior was far away. So that's kind of interesting because the error will be smaller, but can we really say this is better estimate? And another interesting outcome from this error flow filter is it looks really, really nice, like a banana shape. That's what we expected for the unimodal case, but for this multimodal case with the two multimodal which is far away, the priors are far away, this is actually not really good because if you see this, the mean should be located somewhere between target and radar. So it looks good, but it's not really good eventually, apparently. But anyway, the feedback particle filter didn't really work for this case because there were some errors for the multimodal case. For the random prior sample set cases, the tendency is more or less the same as the LCD case, the deterministic sample case. So local exact diamond Hong and particle flow particle filters, and Gromov flow, and oopsie. The same. Anyway, so here's the quick summary. We provide a guide to the galaxy of the particle flow-based filters. And then there are three main branches. So if you want to implement in your own system or on your problem, you can have a look on especially Newton flow particle filter, Gaussian flow, and maybe Gromov flow and the error flow filter. And feedback particle filters are maybe you can just have a look on the diffusion map one because constant gain one didn't really work well for some cases. And here are the conclusions of this part. Newton flow works well with the LCD samples, but not really well with the random samples. And the performance of the DHFs can be limited due to the auxiliary filter that we used, in this case, EKF. And EDH fails when the reference Jacobian has zero components. So in this case, the x2 direction wise, the Jacobian has zero. And particle flow particle filters shows quite overconfident result, which is not ideal. And Gromov filters quite interesting and promising. If error flow filter as well work quite well, but biased. And we are working on the extended literature survey. So now we're presenting this one next week in a conference, but we want to work on some journal paper and then hopefully can show the word of this guidance so everyone can just read it and then one can implement it easily. But obviously there's some limitation of our current work, which was only qualitative evaluation is considered, not even any error metrics or like computation as well. So those really need to be considered it's already considered in the extended literature survey, but we just didn't have a solid result at the moment. And evaluation in the higher dimension problem should be done as well. And yeah, some other sensitive analysis like a number of samples or step size selection must be included as well. That was actually the first part of the presentation. How much can I talk more? Like 10 minutes is okay, or five minutes, or within 5 minutes is fine. I'm sorry, but please allow me to make this presentation really quick in 5 minutes because there's not really many things in here. Anyway, so this is, as you could see from the previous case, when the prior itself was random for the Newton flow particle filter, it didn't really work well. So what we wanted to do here was we want to do the time prediction step or propagation step, and then we want to make it deterministic, like this on the right hand side. So that was the idea. We started this one. Was presented in the Fusion 2026 in Trondheim. I will just go quickly and then you can have a look in detail in the papers. So, so there are three approaches we proposed. The first one is one-to-one addition with the permutations, where we just simply said OAP. So let's say we have a propagated samples, time propagated using the dynamics. And then we need to, when we use the particle filters, we need to add the noise to this sample set because there's uncertainty in the time propagation or dynamics that we use. So in the normal particle filter, we just simply add the random noise, but we just didn't want to use the random noise, but somewhat deterministic matters for like an optimal error we wanted to use. So in this case, we sample the deterministic noise set and then we add it to the each samples. And the next time step, so it is still kind of look random at this time step, but we permute this deterministic noise set and then add it to the each samples again. So if you see in a long term, if you do the multiple time propagation, it actually becomes getting closer to the optimal sample set instead of using just simple random sample addition. That was the one idea. And the other idea is we want to use the moment matching. So we have a noise samples because we know the uncertainty of this dynamics model. So we want to add these propagated samples to the noise samples and then just match the first two moments of this addition so that we can have the nicely slightly spread deterministic prior set from these two sets. And the last one is reduction from a deterministic observable set, which is quite simple and easy idea. So what we want to do is we want to add the deterministic noise to each samples. So like if we start with the 10 samples and if we add like a 5 noise to the noise sample set to the each samples, and it becomes like 50. Yeah. And then we want to reduce it back to 10 samples using the reduction step. And the reduction step, we simply calculate another new sample set and then we just minimize the distance between these two while keeping the mathematical properties of this sample set. So anyway, that's the main idea of this approach. And then we just move on to the result. The scenario we tested for this case was this interesting robot kidnap example. We just wanted to make it as a tracking problem. So it's not really robot kidnap, but kind of similar because the robot starts from here and then moves on to here, and then there's a sudden change of the position and velocity, and then the dynamics changes. So we consider this example. EKF failed, particle filter failed, but the approach that we the proposed approach it quite worked well. Like this, blah blah blah, and then if we move on to some numbers, here we have numbers for the 1,000 Monte Carlo runs. Obviously, EK was computationally most cheap, let's say. So prediction time was smaller, much smaller, and the run time was much smaller compared to the other ones. But if you see the average RMSE, the proposed ones are much smaller than the EKM particle filter, and especially the OAP, the one you mentioned in the very beginning. We optionally adding the noise and then the permutation. That one shows the smallest error. And computational wise, the reduction step requires the optimization and is way too expensive. So it was not really available for the real-time case, but the other three was available for the real-time applications. So the conclusion is what we derive from these example cases actually fully deterministic case for this kind of example will not be really beneficial, but somewhat has some sort of uncertainty, or sorry, sort of randomness and sort of deterministic, but in the long term is close to the optimal, might be the good approach for this kind of example where there's the jump. But future works, again, the result provides a baseline, but limited to the single scenario because I just tested one scenario, the Monte Carlo simulation. Ablation study and the sensitive analysis is required, and evaluations across diverse and high dimensional scenarios will be required as well. So that was it. Thank you very much. If you have anything you want to discuss, you can send me an email or you can connect on LinkedIn as well. And thank you very much. And feel free to ask any questions if you have. Pleasure. Yes. Um, yeah, that's a really good question. The idea is we want to use this gamma steps to generate the flow. And then if you just do it in a one-time step, there'll be a huge jump because, for example, if we have like prior, but when the likelihood is only located in the tail of the prior, then if you use the samples, these will not be able to consider for this step because the innovation will be huge. So that instead of we use this huge jump, let's make it divide it into small steps and then do it like very slowly and a little by little. That's kind of intuitional way of explanation. Thank you. Like like if we have a prior like this, and the likelihood is only like this, very picky one, then and then we want to use the samples, and then we have multiple samples here, maybe only one or two here. But then the innovation term here is way too big. And it's almost impossible to bring these all the way to here. So we just want to kind of flatten this likelihood like this so that we can move these samples little by little to like whatever posterior we will have. I mean, the posterior will be somewhat like this or something. Instead of resampling it, just getting exactly, yes. Yeah. So we don't have a resampling step for these particle flow-based filters. Yeah. You can think of in a that way, but not really resampling in the importance sample importance resampling. Not like changing the weight, but like moving in a freshly sampling again. Yeah, you can think in that way. Yes, exactly. Yeah. Yeah. My pleasure. My pleasure as well. Yep. Yeah. I have a question about why kit Mhm. that you mentioned showed Mhm. Maybe this one. Right. It's quite obvious because the biggest difference between these two, the local EDH and then particle flow, particle filter with LEDH, is the left one just let the flow move the particles and just say that that's already posterior. But particle flow, particle filter assumes the result of the flow as the proportional density, which means there'll be another weighting, importance weighting step using the measurement. So to be honest, I'm not really sure, but it almost sounds like they use the same measurement twice because they do the flow using the measurement to make the proposal density and then do another weighting step using this measurement. So it's kind of if you really see this as like we use the same measurement twice, then it's kind of obvious that it shows the overconfident, which is look almost exactly like the likelihood we seen in the beginning. Yeah.
Well, then, other than avoiding
Mhm. Mhm. Mm, very good question, but I didn't really think very detailed about this one. Mhm.
in many practical
Mhm.
while sacrifices.
Mhm. There's another thing I can actually tell you, which is slightly different but aligned in your question. So let me explain really quick history about this particle flow filter from Dam and Huang's group. So Dam and Huang, they're actually working for Raytheon. So probably you already know this company, Raytheon. I think they make towers. So they're a defense company in the US. And the reason they proposed this one is EKF is not good enough. But particle filter is way too expensive computationally. So they wanted to find something else in between. We don't really want to use that many number of particles for the particle filters, but we want to find something else work better than EKF. And that's how the particle flow filter from Dam and Huang's group were proposed in the beginning. So I can answer your question in this way. It's still more computationally expensive, more expensive than EKF, but works better than EKF or more or less the same, but is much cheaper in terms of computation compared to the particle filter because they can use much smaller number of particles compared to the particle filters. Yeah, maybe that could be a kind of answer to your question, I think.
Another point,
Yeah.
right?
Mhm.
Um, well, to give you a bit of context, he got it work for another this, this
Uh,
BSc and MSc.
yeah, right. Yeah.
Anyway, he second and it was by and other words. So I always
Mhm. Okay, so I guess this is toughest question I ever asked in my entire career life. I'm joking, but um, well, what I'm trying to do is whenever I do this kind of survey or review, I'm just trying to make kind of tree or like hierarchies, classifications of these older papers, and then like just like the figure that I showed in the beginning, like particle flow filters, tree groups, and different algorithms, something like that. So what I'm trying to do is just to categorize them in my head and then make it in the visual figures. You know, I actually don't know. I mean, maybe I was just lucky that I got awarded, but yeah. So that would be kind of one way you could try, like maybe try to make it visualize. Because as a researchers, sometimes we miss the bigger pictures, and then we just dig into the very detail of the each papers for each research topics. But maybe someone like me, or trying to see the bigger picture. I'm not really good at digging very in detail, but maybe I'm okay in seeing the bigger forest, let's say. So maybe I think it's really nice for the researchers. You definitely need to see the details, understand, and then make a deeper research, but at the same time, always keep your eyes wide open to see the forest at the same time, maybe. That's definitely required for the researchers, I think. Yeah, pleasure. I thank you.
Otherwise,
Sure. My pleasure. Thank you very much. Thank you.